Although aircraft may differ in design and performance, the aerodynamic forces acting on any maneuvering aircraft are basically the same. An understanding of the aerodynamics of maneuvering flight will help you develop the skill to perform precise maneuvers while operating your airplane within its design limitations. In straight and level unaccelerated flight, the forces acting on your airplane are in equilibrium. In a stabilized climb, the forces are also in equilibrium. However, the relationship between these forces is changed. When pitch is increased and the flight path is inclined, the force of weight is divided into two components. One component of weight opposes lift 90 degrees to the flight path, and another component acts in the same direction as drag, opposing thrust. Thrust also is divided into separate components, one which acts parallel to the flight path and the other which acts perpendicular to the flight path. The total thrust required is greater in a climb than in straight and level flight. Unless thrust is increased through an addition of power, airspeed will decrease as the pitch attitude increases. To maintain the airspeed, the transition from level flight to a climb normally requires a change in both pitch and power. Once pitch attitude is established and power is properly set, the airspeed and rate of climb will stabilize. During high-power, low airspeed flight conditions, such as those present in a climb after takeoff, several forces can act to create a noticeable left-turning tendency in propeller-driven aircraft. One of the forces, known as torque, is simply Newton's third law at work. For every action, there is an equal and opposite reaction. The force required to spin a propeller clockwise, as viewed from the cockpit, acts on the rest of the airframe as a force in the opposite direction. In other words, the airframe will rotate counterclockwise or to the left about the longitudinal axis. Gyroscopic precession also causes a left-turning tendency. The aircraft's propeller exhibits the same characteristics as a gyroscope: rigidity in space and precession. Precession produces a left-turning tendency and is most noticeable when the nose is pitched down, such as when a conventional gear aircraft raises its tail wheel during the takeoff roll. As the nose of the aircraft pitches down, a force is applied to the top of the propeller arc. This results in a force exerted 90 degrees in the direction of the propeller's rotation and causes the aircraft to yaw to the left. Another left-turning tendency, known as asymmetrical thrust, or P factor, is most pronounced when the engine is operating at a high power setting and the airplane is flown at a high angle of attack. When the propeller's plane of rotation is perpendicular to the relative wind, the ascending and descending propeller blades have equal angles of attack and produce equal amounts of thrust. As the airplane pitches to a high angle of attack, the descending blade of the propeller has a higher angle of attack than the ascending blade. The result is that more thrust is produced by the descending blade on the right side of the airplane, causing a turn to the left. Spiraling slipstream, which also produces a left-turning tendency, is the result of the airflow behind the propeller moving rearward in a corkscrew motion around the fuselage. Since the propeller is rotating clockwise, the slipstream pushes the vertical stabilizer to the right, causing the nose of the airplane to yaw left. To help counteract left-turning tendency and make the airplane easier to control, some manufacturers have incorporated special design features. One such feature is a small metal tab positioned on the trailing edge of the rudder. The tab is bent slightly to the left, so the pressure of the passing airflow pushes on the tab, forcing the rudder to the right. This creates a yawing moment, which counteracts the airplane's tendency to turn left. In stabilized descending flight, like a stabilized climb, the aerodynamic forces acting on the airplane are in equilibrium. However, during a descent, one component of weight acts perpendicular to the flight path, opposing lift, while the other acts forward along the flight path, adding to thrust and opposing drag. If the power setting is unchanged, airspeed increases as the nose is lowered in a descent, and a corresponding increase in parasite drag works to balance the force of weight. When airspeed stabilizes, aerodynamic forces are again in equilibrium. If the force of thrust is removed by reducing the power to idle, the forward component of weight must be increased to counteract the force of drag. In order to maintain the same airspeed, the nose must be lowered even further. In a gliding descent, the best glide angle and the best glide distance result from flying the airplane at an angle of attack which provides the least amount of total drag for the corresponding lift. This angle of attack is referred to as the maximum lift-to-drag ratio, or LD max. The aircraft's best glide speed normally is achieved at the angle of attack corresponding to LD max. The best glide speed is published in the pilot's operating handbook. For example, the best glide speed for this airplane at 2,600 pounds is 75 knots with the propeller windmilling, flaps and gear up in calm wind conditions. Glide ratio represents the distance an airplane will travel forward without power in relation to altitude loss. For example, a glide ratio of 10:1 means an airplane will travel approximately 10,000 feet of horizontal distance for every 1,000 feet of altitude lost in a descent. The angle between the flight path and the horizon is called the glide angle. As drag increases, so does glide angle. For example, in a glide when the landing gear is lowered, there is a corresponding increase in drag. To maintain the same airspeed, this increase in drag is counteracted by lowering the nose of the airplane, thus increasing the glide angle, which results in a reduced glide distance. Although the weight of the airplane doesn't affect glide ratio, it does affect the airspeed that must be flown to attain the best glide distance. Since a heavier airplane will sink faster, a higher airspeed must be maintained to support the greater weight and yield the same glide distance as a lighter airplane. Turning flight introduces new concepts with respect to the aerodynamic forces acting on the airplane. In a bank, total lift is divided into two components. One acts vertically to oppose weight, and the other acts horizontally to move the airplane in the direction of the turn. Since the vertical component of lift is reduced in a turn, to maintain altitude, you must apply back pressure on the yoke to increase the angle of attack until the vertical components of lift and weight are again equal. The horizontal component of lift creates centripetal force, which acts toward the center of rotation. During the turn, this center-seeking force works to oppose inertia, which is the tendency of the airplane to continue in a straight line. As the airplane enters a turn, the aileron on the inside of the turn is raised, and the aileron on the outside of the turn is lowered. The lowered aileron increases the angle of attack and produces more lift for that wing. Since induced drag is a byproduct of lift, the outside wing also produces more drag. This increase in drag causes a yawing tendency toward the outside of the turn known as adverse yaw. When you enter a turn, you should depress the rudder in the same direction of the turn to help compensate for adverse yaw. Once you are established in the turn, you may neutralize the ailerons to prevent further roll. Since the cause of adverse yaw is removed, rudder pressure also can be relaxed. When you roll out of the turn, you should apply coordinated aileron and rudder pressure in the opposite direction of the turn to return to a wings level attitude. During a turn, the outside wing travels faster than the inside wing and creates more lift, which may cause the airplane to continue rolling beyond the desired bank angle. You can correct this overbanking tendency by applying a small amount of aileron in the opposite direction of the turn. Two terms which are used to define the performance of an airplane in turning flight are rate of turn and radius of turn. Rate of turn is the amount of time for an airplane to turn a specified number of degrees. Every aircraft will turn at the same rate when flown at the same airspeed and angle of bank. If airspeed is increased and the angle of bank remains the same, the rate of turn will decrease. Conversely, a constant airspeed with an increased angle of bank will result in a faster rate of turn. The radius of turn, or the distance an aircraft must be flown to complete a turn, is also dependent on airspeed and angle of bank. For example, when airspeed is increased and the angle of bank remains the same, the radius of turn increases. However, if the airspeed remains the same and angle of bank is increased, the radius of turn is smaller. Load factor is the ratio of the load supported by the wings to the actual weight of the airplane. An airplane in straight and level unaccelerated flight has a load factor of 1, which means the wings are supporting only the actual weight of the airplane and its contents. You may be more familiar with the term G-force, which is used to describe loads imposed on a maneuvering aircraft. You can relate G-force to the feeling you get while riding a roller coaster. As you enter a banked turn on a roller coaster, you feel the forces created by the combination of centripetal force and inertia as seat pressure. The pressure you feel is, in reality, an increase in load factor that is expressed in Gs. As the roller coaster reaches the top of the track and begins a rapid descent, you may feel a sensation of weightlessness if centripetal force and inertia cancel each other out. It's important to note that a change in load factor can occur at any time due to pilot control input or environmental conditions such as turbulence. The amount of stress which an airplane can withstand before structural damage or failure occurs is called the limit load factor. Most general aviation aircraft are certificated in one of 3 categories: normal, utility, or acrobatic. Many general aviation airplanes are certificated in the normal category, with a limit load factor of 3.8 positive Gs and 1.52 negative Gs, which is sufficient for basic training maneuvers. Airplanes which are certificated in the utility category have a limit load factor of 4.4 positive Gs and 1.76 negative Gs. Acrobatic airplanes are even less restricted, with a limit load factor of 6 positive Gs and 3 negative Gs. Regardless of the category, it's very important to adhere to proper loading techniques and always fly within the limits listed in the pilot's operating handbook. Another way to avoid possible damage to your airplane by excess loads is to observe the design maneuvering airspeed, or VA. Related to stall speed, this is the maximum speed at which you can use full or abrupt control movements without overstressing the airframe. VA is normally not marked on the airspeed indicator since it varies with total weight. Maneuvering speed decreases with a decrease in weight because an airplane operating at a lighter weight is subject to more rapid acceleration from gusts and turbulence. If G loading increases while operating below maneuvering speed, your airplane will stall before the limit load factor is exceeded, thus avoiding potential damage to the airplane. Understanding the forces acting on your airplane will improve your ability to perform more complex maneuvers with greater accuracy and safety as you progress through your flight training.